Hello everyone. In this session, we are going to learn about the transportation and assignment problems. The transportation problem is an important class of linear programming problems. The idea is to find the least cost solution to transport a commodity from a number of origins to multiple destinations. Although the standard simplex method can be used, due to special features of the case, the problem can be solved more effectively with some customized procedures. In this session, we will mainly understand the principal concepts of the procedure involved. However, the actual calculation part is not covered. Interested students may refer to the further reading material which has been provided. The session also covers the assignment problems, which can be converted into a transportation problem and then can be solved using the associated procedures. Let's begin with description of transportation problem. The transportation problem consists of solving the problem of how to transfer products from m number of origins to n number of destinations. So the origins could be warehouses and the destinations could be factories which require the products from warehouses. Let's understand the terminology. Each of the warehouse can store certain amount of product. Let's call that product, that quantity as AI, where I indicates ith origin and AI indicates quantity which is available at ith origin. Similarly, at the destination, we are representing Bj as the quantity which is demanded by jth destination. The cost involved in transporting a product from ith origin to jth destination is called as Cij. So this is from ith origin to jth destination. The cost required is Cij. The quantity which is getting transported from ith origin to jth destination is called Xij. Now the transportation problem is finding out the values of Xij's such that the total cost of transportation is minimized. Let's put this problem in a more standard linear programming format. So what we are talking here is from every origin, certain quantity will be transported to different destinations, and each of this transport will involve certain amount of cost. If we add up all the costs involved from different destinations to different origins to different destinations, we will get the total cost. So that is the objective function which we are trying to minimize, which is given as double summation of Cij multiplied by Xij, where Cij is cost of transporting product from ith origin to jth destination, and Xij indicates the cost which is involved in the quantity which is to be transported from ith origin to jth destination. There are constraints on this particular problem in the linear programming terminology. The first constraint is that the summation of Xij, j running from 1 to n, that is from ith origin, whenever you are transporting a product to different destinations, the total quantity which is available should be higher than what is demanded. So from ith destination you can supply to various ith origin, you can supply to various destinations. The summation of quantity supplied to various destinations should be smaller than what is available at the origin, and this is for I number of origins. Similarly, for destinations, each of the destination is demanding a quantity which is given by Bj. If you sum up the quantities which is received from different destinations, it should be higher, that is the origin should be able to supply the quantity which is more than what is demanded. So this is the two constraints which are there on this transportation problem. And of course the quantities cannot be negative. So all the quantities, the unknowns which we are trying to find out, they are positive. As we can see here, the constraints are of inequality type. So we can convert them into a standard linear programming type by introducing the slack variables and the artificial variables. So by introduction of slack variables and artificial variables, we can convert this into a standard linear programming form or the equality form, and then solve using the standard linear programming methodology. However, the nature of the transportation problem makes it easier to solve with a different type of approach that we are going to discuss next. Before that, let's see how these inequalities can be converted into equalities. A special type of transportation problem known as balanced transportation problem, in which case the total number of quantities which are available at the origins matches exactly with the total number of quantities demanded by the destinations. So in this particular case, all the inequality constraints gets converted into equality constraints, and this is known as a balanced transportation problem. But as we can imagine, this is rarely going to happen in real life. So we need to have some approach which will convert these inequality variables to equality variables, so that the problem, as you can see here, is in the standard linear programming format, and then we can apply the methods which are available. So let's consider two scenarios. The first scenario is that the total supply is greater than total demand. That means the quantity which is available at the origins is larger than the quantity which is demanded by the destinations. In this case, rather than using additional variables, a standard trick that is followed is you add a dummy destination. So you add a dummy destination, also known as a sink, and the cost of transporting to this dummy destination is considered as 0. So the cost of transporting to this dummy destination is 0, and whatever surplus quantity which is there in the origins, so that is given as demand of the dummy destination. So in this way, by introducing one destination station, we can convert this problem into a balanced transportation problem, and the format of the equations become useful for the linear programming problem. Now let's consider the scenario which is opposite to what we have seen, where we are talking about the case where the total supply is smaller than the total demand. So in this case, the quantity which is available at the origins is smaller than the quantity which is to be supplied at the stations. As you can extrapolate from the previous approach, in this case the strategy is opposite to what we did here. So in this case, we'll add one artificial source. So we are going to add one artificial or dummy source and attribute the surplus demand. So surplus demand is attached to this dummy source, and the cost of transporting from this dummy origin to the different part is considered as 0. So in this way, we can convert the problems which are of inequality type or unbalanced transportation problem into a standard transportation problem. Once the problem is brought to balanced transportation problem, the techniques of transportation problem can be applied to it. Let's see how it is done.